Hi, and welcome to the next video in the Modern Physics series. Today we're going to be talking about the Compton effect and X-ray scattering. The initial question that we're going to answer is, what happens to the frequencies of X-rays after they are dispersed? And that is usually when they go through an atom. We find that the answer is very simple. X-rays scatter depending on their location. They have a lower frequency than when they were emitted. So that's the question. Why does an X-ray coming in come out at a different and lower frequency? Where did all that energy go? Here we have in front of us the electromagnetic spectrum that comes from the reference table, and I want to point out to you that X-rays are very highly energetic rays that are beyond visible light, cannot see them with our eye, and they are up here in the order of magnitude of frequency from 10 to the 16th all the way up to say 10 to the 20th. The wavelength of light, as you know, decreases as you go from radio waves to microwaves to X-rays and all these colors in between. Now we call them colors even though we cannot see them. So as you increase in frequency, you decrease in wavelength. So the premise of this problem is that an atom is struck with X-ray light. Now that's invisible light, but what comes out on the other side is visible light and an electron. Let's discuss how that process works. As I mentioned, high energy X-rays strike the atom and they hit the electron and they knock it out of the orbit. And the energy that goes in, which is invisible light, part of it comes out as visible light and an electron comes out. And we want to be able to account for the energies of the electron's kinetic energy and the new visible light's energy. The process is called scattering because the X-ray energy is scattered between the ejected recoil electron and the emanating ray of visible light. The visible light has a longer wavelength and therefore a lower energy. So the original X-ray turned into a lower energy ray of light or a lower energy photon. That part is called the Compton effect. And the ejected electron, that is the scattering effect. So there's really two experiments going on at the same time, but when you examine both of them together, you come to realize that both pieces add the energies back to the original X-ray. Let's take a look in the next slide. We can see that the X-ray photon has a very short wavelength and therefore a high frequency and therefore a high energy. It hits this electron that's in the orbit around the nucleus and it ejects it from the orbit. And the kinetic energy that's developed by this electron is actually borrowing some of the energy from the incident X-ray photon. Then, when some of that energy is taken away from that X-ray, it loses energy and it continues in a deflected path with less energy. Less energy translates to a longer wavelength, and in this case, it brings the wavelength down into the visible range. The kinetic energy of the electron can be measured in something called a cloud chamber, and that is an experiment that we will talk about in detail in the next video. Right now we're going to talk about the energy of this photon of X-ray light being converted down into the energy of a visible light. The process of energy exchange is quite simple when you look at it from the quantum point of view. A photon of X-ray quality or X-ray energy strikes the electron and then it disperses and gives a portion of its energy to that electron in the form of kinetic energy, and then the remainder of the energy, what's left over, and then the X-ray has less energy and therefore it becomes a scattered photon, usually in the visible light spectrum energy range, somewhere in the blue-violet range. The total energy of the system is quite easy to calculate. You just add up the kinetic energy from the electron plus the energy of the visible light and you get back to the total energy of the incident X-ray. This experiment helps us quantify the momentum of light, and if you recall that the momentum for any particle is mass times velocity, where the rest mass of light equals 0. So how does light, or a photon of light, have momentum? And that's because it's related to the amount of energy. P equals hf over c, or h divided by lambda. So even though the rest mass of light or a photon has no mass, you can still have a momentum value for a photon based on this experiment, and these are the results. P equals hf over c. So it's the energy divided by the speed of light, or the Planck constant divided by the wavelength. So even though Arthur Compton discovered the effect that we now call the Compton effect, and that is the decrease in frequency of the X-ray from X-ray energy down to visible light energy, Wilson and Booth were able to measure the kinetic energy of the ejected electron in something called the cloud chamber experiment. Since the ejected electron is a tiny mass, they sent it flying off in a supersaturated solution that would create a cloud as it zoomed through it. The electron passes through the supersaturated solution. It acts as a condensation nuclei, so the supersaturated air has some place to condense. And when it does that, it creates these cloud streaks. The cloud streaks allow us to actually see the path of the electron as it passes through the vapor. In this picture, you see a cork with a pin, and on the end of the pin is an alpha source, and the alpha source has particles that are emitting alpha particles coming off the end of the pin. And since the particle acts like a condensation nuclei inside the supersaturated vapor, you get these little cloud trails. That helps us to see the direction that the electron is being ejected. In a more sophisticated setup, these electrons then are measured as they impact the wall, and they use something called a stopping potential. Measures how much energy it took to stop the electron, so therefore that energy is directly correlated to the kinetic energy of the experiment, and that's how the two experiments work hand in hand. So going back to the original picture, it's this simple. We have the X-ray photon passing into an atom. It hits an electron. The X-ray loses energy and gives some of it to the electron, which ejects from the outer shell. The electron has kinetic energy that is measured in the Wilson and Booth cloud chamber experiment, and the scattered photon lowers its frequency, elongates its wavelength, and displays itself usually in the form of visible light, which can then be detected by a spectrometer. That's the Compton effect and X-ray scattering. I hope you enjoyed this lesson, and we'll see you in the next video.